So thank you for your interest in my presentation about a proven solution to reduce the transfer of structure-borne sound and couplings. My name is Nora Yazdandoost and I'm working for Geislinger here in Salzburg. I will start my presentation with an example of a marine powertrain. We will look at the main parts of the marine powertrain, and I will give an overview about the Geislinger products and the task of them. Afterwards, I will explain the theory behind structure-borne sound, and especially the measurement of structure-borne sound in systems. And the focus in this presentation is the dynamic stiffness. So we will look at the dynamic stiffness, how it gets calculated, and what is the meaning of these. To understand dynamic stiffness better and the influence of each parameter inside the dynamic stiffness, we will look at a single mass oscillator and discuss the parameters. With the gained knowledge we get out of these, we will see the advantages of the Zelenko coupling, which is a Geislinger product. So there are more and more demands on shipping, and to protect marine environment and people in port regions, monetary incentives has been made to create ships as quiet as possible. Geislinger offers at different points in the powertrain solution to reduce the structure-borne sound. And in this example, the gray components are just elements of the powertrain and the red ones are Geislinger products. And for example, the engine is double elastic mounted and the gearbox is just elastic mounted. So between both of these parts, a misalignment coupling needs to be installed. The same is with the electric engine, which is shown here, and the gearbox. And there's also the need for a misalignment coupling. And in the propeller shaft is the Zelenko coupling, which is the main part of this presentation. At the open end of the engine is a steel spring damper to reduce the torsional vibration of the system. And on the other side of the engine is a combination of a misalignment coupling and a steel spring coupling to reduce the vibration in every direction, not just the torsional vibration. Every product from Geislinger is designed and adapted individually for each case. This is important. I will show you later why. So on the next slide, we will focus on a simplified example with the Zelenko coupling. Firstly, structure-borne sound means every sound that goes through a solid body. Structure-borne sound can be perceived for humans as vibration or as radiated airborne sound. And it is always just a relative value. So structure-borne sound depends from the measuring points that has been taken. It's no absolute value. This is also important. In this example, we have an elastic-mounted engine, which is shown here, the Zelenko coupling and the gearbox. And of course, the engine is the sound source in this example. There, it's generated airborne sound as well as structure-borne sound on which we focus. And structure-borne sound has two different transfer paths of the system. The first one is the red one, the primary way, which goes from the engine through the mount into the foundation of the engine, and the ship hull and the passenger cabins where vibration or radiated airborne sound can be perceived. This transfer path is absolutely determined from the spring stiffness of the mount. The secondary transfer path is the blue one, which goes through the powertrain and the coupling, of course, into the gearbox, the foundation, and the ship hull and passenger cabins. So to reduce the secondary transfer path, the coupling needs to reduce the structure-borne sound. So structure-borne sound, as I told, need two measuring points, and a common way is to measure the input wave in the system and the output wave of the system. So sensors before our coupling and after our coupling get installed, and on the left side is a list of the sensors, of common sensors. They are, for example, acceleration sensors. They are very inexpensive and easy to install. And beside acceleration, they can also measure velocity and displacement, of course. Then there are force sensors, which are way more expensive and not that easy to install. Most times they need a fixed side of the test object. If there's a need for contactless measurement, optical sensors can be used. So we have in-house laser vibrometry, which is a laser which measures on defined points the interference and get the surface velocity out of these. So as I said, we need two measuring points, which leads to a transfer function. And there are different transfer functions. The most common is the transmission loss function, where two acceleration sensors are used before and after the test object. Then there are various combinations of displacement, velocity, acceleration, and or force. But interesting for Geislinger is the dynamic stiffness. Dynamic stiffness is defined by the displacement at the input and the force at the output. As I already said, transfer function depends from the measuring points. There's one exception. The exception is the dynamic stiffness. So we will look closer to the dynamic stiffness. We have in Germany the standardization DIN and ISO. And the DIN and ISO 10846 enables us to build or design a test bed where the dynamic stiffness, which is measured, is independent from the test bed. So it's possible to compare products between companies or products of different test beds if the test beds are designed after the standardization. That's the reason for our focus on dynamic stiffness if we want to talk about structure-borne sound. The structure-borne sound is calculated by the logarithm of the force with the standardization at the output and the displacement at the input. And to get the result, we are getting, of course, a diagram where the dynamic stiffness is shown over the frequency. And because of the excitation displacement and the force at the output, at eigenfrequency, the system has their eigenmode and a higher force, and of course a pierce occurs, so we have here an eigenfrequency of the system. I will come back to the known example with the simplified engine coupling gearbox system, and this can also be simplified by a point mass and spring elements as mounts and as the coupling. And even our coupling is a multi-mass oscillator. So we have the flexible membranes, we have the intermedia shaft, and it's getting complicated. So I've designed a single mass oscillator to look at the parameters. And we have here the mass, a spring element, damping element, an harmonic excitation force, and as a response we have the displacement. And here are some equations. They are not that complicated. And the first line is the basic equation of motion. So the only relevant parameters is the force, which acts here, the force of the mass, of the damper, and of the spring. So the relevant parameters are mass, damper, spring stiffness. And the second line is the stiffness defined, of course, and then there are some acceptance. I will ignore the damping at the beginning. We have already heard in the presentations before me that the damping only acts in the eigenfrequency and won't change the dynamic stiffness over whole range. Also, because of the harmonic force as extinction, we have the response, which is a harmonic displacement and acceleration. In this line, the stiffness of the mass parameter and the stiffness of the spring parameter is calculated. And at the end, we get the total dynamic stiffness here, which is defined by the sum of the absolute value of the sum of the terms from the mass and the spring stiffness. So we have a system which only depends over the frequency from mass and spring stiffness. And I've done a simulation with a point mass of 60 gram and a spring stiffness of 1 million Newton per meter. And I've done the simulation in ANSYS, and out we get, of course, this dynamic stiffness without damping. Yes, we have the frequency on the x-axis and the y-axis dynamic stiffness. And the system has an excitation of the force. So, of course, the eigenfrequency will occur as a minimum, as you can see here. So to understand better the influence of the mass and the spring stiffness, I've also plotted the transfer function only of these terms. The orange graph is the spring stiffness, the green one is the mass stiffness. And I will start with the spring stiffness. It is shown that the spring stiffness of the system defines the total dynamic stiffness at the beginning until the first eigenfrequency. So, and the eigenfrequency itself, the mass stiffness and spring stiffness are trimming each other, cutting each other. And after the eigenfrequency, the mass stiffness is the relevant parameter on which the total dynamic stiffness depends. So the learning out of these is that we need to influence spring stiffness and mass in a system if we want to reduce the dynamic stiffness. Otherwise, we will just act before or after the eigenfrequency. As I told before, I have also simulated a damped system, which is shown here, the gray graph. And the eigenfrequency is less developed, but the dynamic stiffness over the range from 40 to 1000 Hertz hasn't changed. So that's the effect of the damping. To understand the influence even better, I have done more simulations where I compare the initial state, the black graph, with changed mass and spring stiffness. And the green graph is a system where I have used half of the point mass, so 30 grams. And it is seen that at the beginning we haven't any change because we have just influenced the mass but not the stiffness. The eigenfrequency will shift into a higher frequency because of the lower mass, and the dynamic stiffness after this eigenfrequency is 6 decibel lower than the initial state. If we only change the stiffness of the spring stiffness of the system, we can see here at the beginning of the dynamic stiffness that we are 6 decibel lower with the dynamic stiffness. The eigenfrequency comes through a lower frequency, but the behavior after this eigenfrequency is just the same as the initial state. We haven't changed there anything. And if we reduce stiffness of the spring and mass the half, then of course the eigenfrequency will stay the same as it's seen in the red graph. And the whole level of the dynamic stiffness will get 6 decibel lower. And we have a Geislinger product, which is a light-weighted composite material coupling with very low stiffness. So we try to find a product which fulfills these learnings. And if we go back to this example, we have the powertrain, we have the primary transfer pad, the secondary transfer pad, and our coupling inside of these. And if we want to know how much structure-borne sound goes through the second transfer pad, the blue one, we need to know the dynamic stiffness of our coupling. So in this black frame is the coupling. And we have test beds at our company. We have 2 test beds, a small one where we can measure couplings with a diameter of 1 meter and get dynamic stiffness as well as the transmission loss function, and a huge test bed where we can measure couplings up to 2.30 meters. But we have to use the small one, and we have to calculate the displacement at the input of our coupling and force at the output of our coupling to get the dynamic stiffness from this coupling. We wanted to compare it to another system, and for this reason we have also measured a steel flank, what would be the case if there's no coupling between engine and gearbox. So here are the results. We have the dynamic stiffness normalized from 0 to 1 over the y-axis, and we have the frequency range until 1000 Hertz. The black graph is the steel adapter we have measured, and the red graph is the Geislinger coupling we have measured. And it is shown that the level of the dynamic stiffness is significantly lower over the whole frequency range. That means that we can reduce the dynamic stiffness in the system, and we can reduce the structure-borne sound which goes through the secondary transfer pad. So I will come to my conclusion. Firstly, the results out of the single mass oscillator. We have seen that damping only acts in the eigenfrequencies. It won't change the dynamic stiffness over a whole range. Also, it is important to understand that we can't use a system with very low spring stiffness but high mass, because we will only influence the dynamic stiffness before the first eigenfrequency. Also, we need to reduce the mass to have a low dynamic stiffness after the first eigenfrequency. So necessary requirements we get out of these is the need for individuality. I have mentioned this at the beginning. We can design and develop couplings for each case with the lowest mass impact inside of these and the lowest stiffness. Beside these, geometry, of course, should be used which bring less stiffness into the system, and we using lightweight materials. So based on this finding, Geislinger will continue to develop products which minimize the transmission of structure-borne sound in the powertrain. And with these lower dynamic stiffness, we can guarantee less structure-borne sound in a secondary transfer pad. Thank you very much. Excuse me. So.
Yeah, thank you.